Hey everybody, Bill Sky, the assembly guy. Let's talk about 64-bit file I/O and what does it mean to get to the end of a file. If you remember, if you've taken a C, or if you write in C or C++ or even Java, as you're reading a file, you need to know when to stop. You know, a file is just so big. Let's say you've got 1,000 integers in there. That means the file is going to be about 4,000 bytes long. When do you stop reading? I mean, when do you stop? Well, in C and C, or in C++, I should say, there's an EOF flag. There's an end of file flag that tells you that we're at the end of the file. But what really happens inside? Now, that's what we're going to be talking about. So let's get right to it. All right, now I've created a Linux program here, and it's a lot the same in Windows. So I'm not sure we're going to do a Windows one on. I think we will. But let's take a look at the Linux one first, and then we'll go ahead and do the Windows. And what we're going to do here is we're going to take a look at this assembler language code. And what I did was I wrote a little program that simply writes data out to a file. And this is a 64-bit program. But if you looked at my first video on file input and output, you'll see that there's a lot in common here. We're moving things to the 32-bit registers. And this actually will work on 64-bit. So why not just do this on 64-bit? Well, the reason is because on 32-bit calls, you are limited. You're limited by the size of the file. Like the file cannot be any larger than 4 gigabytes. And you might say, oh my God, that's a huge file. Well, not really, considering really high quality audio files, even pictures these days. I have a Nikon, I think it's a D3 camera, and the pictures are like 8 gigabytes in size. I haven't checked that for a while, but they're huge, right? Also, video files. Video files are really, really big. So on a 32-bit system, you just can't create files of that size. But on 64-bit, you can. So if we're going to be using the 32-bit application programmer's interface for this, we're going to have some challenges. So let's go through what each one of these are going to be. So first of all, the settings that you send to the registers to create a file, and let's go ahead and create the file here. If you see right here, we're moving 8 to EAX. Well, first of all, we have to change everything to the 32-bit or 64-bit registers. And in the case of creating a file, it's no longer 8, it's 85. And I believe it's 85 decimal. I'm not sure what the hexadecimal is, but so it's 85. What goes into the file, or where the file name goes, is no longer EBX, it's now RDI. So RDI contains the file name. And then where do we put the file permissions? We put them into RSI. So those are the file attributes. Now instead of int 80, we're going to do this other thing called syscall. And you may have seen this if you've looked at my other programs using the Komanetsky functions in 64-bit. So we're going to go ahead and do that. Instead of EAX, we're going to look at RAX. Now this is going to see whether or not it opened correctly. There's our error open, and there's our output file, and we have to change that to RAX. So there's a lot of duplication here. On Windows, it's not so much, and you're going to see that when we get to Windows. Now, there's a couple of other things that we have to do. Instead of the output file being a double, which you see it there, we have to make them into quads. So anything that is a 64-bit application that's going to be holding addresses or handles, you always want to make those quads. I believe everything else here is fine. We've got the program name, or we've got the file name. That's a set of bytes. We've got our example string. So that's to open the file. Now to write the file, we've got some more things that we have to change. First of all, and I always like to change it this way. Just change everything to R. Now that doesn't mean that it's going to be is what we're going to use. So RAX. So to write a file, you say 1. The output file handle no longer is RBX, it's RDI. The example string is no longer RCX, it's RSI. And the length of it is now RDX. And again, instead of int 80A, we say syscall. And again, instead of EAX, we're looking at RAX. So we're just changing this to 64-bit. I don't know why they did it this way, but they did change the numbers quite a bit. And then to close the file, we're going to say instead of moving 6 to EAX, we're going to move 3. And the output file handle is going to be RDI. And we forgot the actual syscall there. And that should be it. Now we have a 64-bit program that's using the 64-bit APIs for writing data to a file. So let's go ahead and make that. It works great. Well, it doesn't work. It built fine. Let's go ahead and open this in terminal. Run it. There's our text file. And there's our data. This is an example string used to demonstrate the end of file. Okay, great. So now so that's the difference between 32-bit and 64. Now I will be putting this API notes in the description of the video. So there's a lot there. We're going to go ahead and do that for you. Now let's go ahead and continue on. So that's 64-bit. Now on Windows it's going to be a lot different, and I'll be doing that in another video, a follow-on video. Okay, so let's go ahead and demonstrate what end of file is. I mean, how does the cat program know to stop reading the file? The cat program is a program on Linux that will display the contents of the file. On Windows you'll use the type program, TYPE, but on Linux you'll use cat. When does it know to end at the E? When does it know that E is the last character? Well, that's what we're going to talk about here. And we're going to do it in 64-bit. So what I did was I went ahead and wrote this file to disk, and now what I'm going to do is I'm going to open it up, and we're going to do this all in 64-bit. So let's go ahead. I'm just going to copy all of this because a lot of it is the same. And we're going to say now open and read the file. Okay. Now we don't want to open it for output anymore. We definitely want to open it for input. And the way that you open a file for input on 64-bit is you move 2 to RAX. RDI is the file name. We don't care about file attributes. So what we're going to do is we're just going to move a 0 there. And RDX is not used at all when you open files. It is used when you write and read. So we're just going to leave it there. So that opened it up. Now we're going to say input file name. Okay. So there you go. Now I'm going to go ahead and build this. Whenever I do a lot of code, I always like to build it every time I change a little bit. Okay. So now let's go ahead and read the file. Now what I want to do here is I want to read one character at a time. So, the data, let's go ahead and start from scratch here. We do have to change the close, so let's change from input to output to input. There we go. And now let's go ahead and read the file. Now, I want to read one character at a time. So to do that, I'm going to need a loop, and I'm going to call this the read loop. And we don't know how many characters are in the file. I mean, we could figure it out by doing another syscall and returning the number of characters, but let's do it the long way. So I'm just going to jump to read loop here. So we're not going to use the loop statement. We're just going to jump to read loop. We're going to have a condition inside of it. Okay. So let's go ahead and read a byte. Now, to read data in 64-bit, you use 0. So that's read data. We're going to move into RDI, the input file handle. We're going to move into RSI. Now we need a read buffer. We need to put the data somewhere when we read it, just like we did in 64 or 32-bit. So I'm going to create a little thing here called read buffer. I'm going to reserve bytes. I'm going to reserve, I don't know, 64? Probably way too much, especially since we're only doing one character at a time. Okay, so where are we? Okay, I don't have all my comments. Okay, open the file. All right. So here we are. So we called it read buffer. Okay. So we're going to move RSI. We're going to be the address of read buffer. And we're going to move into RDX1. Now, why are we moving 1? We're going to read one character from the file. And then we're going to say syscall. All right, so let's go ahead and now print the read buffer. So I'm going to push the read buffer address onto the stack. I'm going to move into RAX1. Now, why am I doing this? So I can print them one character at a time using the Komanetsky functions. I'm going to push RAX, and I'm going to call print text. And then I'm going to call print end L. So we're going to say what to print, how many characters to print. Now, print text is a different function than print string. Print string is assuming a zero delimited or zero terminated string, but print text doesn't. Print text takes this other function or this other value right here, this other argument 1, saying how many characters. We're going to go ahead and push that onto the stack, and then we're going to print it. All right, and then we're going to jump to read loop. Okay, looks like that looks pretty good. So let's go ahead and build it. All right, so our program is going to create the file, then it's going to open it for input, it's going to read it one character at a time, and then it's going to close it. Okay, let's take a look at the results. Oh, my goodness, what's happened? Well, it's in an infinite loop, and that's because we don't know what it is. We don't know where the end of the file is, so it just keeps going and keeps going and keeps going and keeps going. So now you might argue with me and say, well, really, did anything print at all? Well, yes, it did. There it is. So I scrolled all the way up. This is an example string used to demonstrate file. Okay, let's go ahead and take a look at what did our string say. End of a file. All right, so that printed out correctly. But it goes on forever. It's never going to stop. And that's because we don't have any kind of a check for the end of file. Now, you do this exactly the same in Windows, so there should be no surprise in there. So there needs to be something here. Before we print the read buffer, we really need to say, did you read anything from the file? And this is how you do end of file. So what I'm going to do is I'm going to say compare for end of file. I'm going to compare RAX with 0. Now, what happens after you read data from a file? The total number of characters that were read from the file, the number of characters read is put into RAX. So if it's 0, guess what? It didn't read anything. So I'm going to compare RAX with 0. If it's equal to, I'm going to say end of file. Jump if equal to end of file. Okay? Now we didn't actually create that label, so let's do that right here. And let's just put a no up there. So this is how you check for end of file. And maybe compare for end of file isn't a good one. So check for end of file. So you compare 0, make sure that it is either 0. Now you could check for less than or equal to end of file. Or jump less than or equal to 0, because it might come back as a negative number. It depends upon the operating system. Let's go ahead and build that. And it certainly looks like it worked this time. No infinite loop, no big deal. So that's how you do end of file when you're reading data from a file in your program on 64-bit. 32-bit is exactly the same. Instead of RAX, you would use EAX. So let's take a look at how we would do this on Windows. All right, let's take a look at the same thing on Windows this time. And what I've got here, I have pretty much the same program. It's the 32-bit version of it. But there's a lot of differences in Windows 64-bit when compared to Windows 32-bit assembler. First of all, there's no such thing as arguments going to prototypes. These are all the 32-bit prototypes for the create file, the close handle, the write file, the read file. So we're just going to delete those. Now these arguments are still used by these functions, but in the 64-bit you just simply don't do it this way. You don't put in the prototype arguments. It's a little bit more like Linux in that case. So what we're going to do is I'm just going to delete all of that. Because if I try to build this, in fact, if I go ahead and save and build this, you're going to see some problems. Let's just do that just as a demonstration. And you see some errors. If I double click on this one, it doesn't know what this comma is there for. And in fact, you don't even need to exit process on 64-bit. So we're just going to go ahead and delete that. Yeah, 64-bit on Windows is a lot more involved when compared to 32-bit than on Linux. So we're going to get rid of that last comma there, and we're just going to get rid of all of these arguments. So you just take care of all those. And we have to remember to get rid of that comma. And because they take up less room now, I'm just going to go ahead and put those all together. Now let's go ahead and build this. All right, we're still going to have some problems. First of all, it doesn't know what invoke is. It has no idea what invoke is all about. And what invoke is in 32-bit, invoke means to run a macro that Microsoft has created that's going to push the arguments onto the stack just like we did, or into the registers just like we did in Linux, and then it's going to call the function. So instead of invoke, you're going to just say call in 64-bit. And you're not going to have a comma after this. So where do the arguments go? There's no arguments that you send to it. What you do is in 64-bit, you put the arguments in registers, okay? Now, in 32-bit, or I should say in Linux 64-bit, it's kind of the same thing. So it's a little bit closer to Linux in this case. So what we're going to do is I'm going to move into RCX. And here's the order in which arguments go. RAX is the first argument. So argument number 1, that goes into RAX. Argument number 2, that goes into RDX. Argument number 3, that goes into R8, believe it or not. And argument number 4, that goes into R9. Any argument after that goes into the stack. So argument number 5, that would go into the stack pointer plus 32. And for 6, 7, 8, you do the same thing. Let's just do 6 and 7. And instead of 32, because each argument is 8 bytes long, we're going to say 40 and then 48. Now, why did they do this? I really have no idea. I believe probably the reason that they did that was because the average function has no more than 4 arguments. I believe that might be why they did it. And so that's why they put them in the registers. And then it's very rare. That's arguable, I would say, because I've had functions that had like 10 arguments in it. I try to stay away from that. But in that case, we put them into the stack. And you don't push them into the stack. That's what's weird. You don't push them in the stack. You put them into the stack based on their position starting at 32. And each one is 8 bytes long. So that's how you do that. So in this case, the file name, the address of the file name is the first argument. So we're going to move that into RAX. And we're going to say offset file name. The next argument would go into RDX. And that's this large number right here. So I'm just going to copy this and paste it. So that goes into RDX. The fourth argument, third argument, which is a 0, that goes into R8. So we're going to put a 0 there. The fourth argument, which goes into R9, that's a 0. And now we've got a few other arguments. I've got this 2, which means create always. I've got this 80, which is normal attributes, and this 0. So that goes into the stack, and you do it this way. You say move a keyword starting at the pointer address, RSP plus 32, and we're going to put I believe that's a 2H. Now I'm going to copy this, and I'm going to change this 32 to a 40, and this 40 or 32 to a 48. And so the next argument is an 80, so we're going to put that here. And the argument after that is a 0, so we're going to put that there. And then you call the function. So now I can delete all of this. Whew! So that's how you call a function, or you call these system functions, in this case create a file, in Windows. And I'll go ahead and build it. So we've got a lot less errors. Things are looking pretty good here. We definitely want to check RAX. We want to check RAX here. And the other thing we want to do is instead of doubles, we want to make these quads. So the output file handle and the input file handle should be quads instead of doubles, because addresses and stuff in 64-bit is 8 bytes instead of 4. So a double word is 4, a quad word is 8. All right, good. So that works. So now we can kind of do the same thing with the other ones, with the other calls. And I think the simplest one is the close a file. So we're just going to say call. And the first argument is the output file handle. So I'm going to move into what was it? RAX? What was the first argument? This is why comments are so important. So move into RAX. The output file handle. And how did we do that up there? Well, we actually didn't do it there. So let's go ahead and move that to there. And if you want to do it like Linux, you can put it in square brackets, dereference it. What kind of errors do we have now? We only have the one error. Awesome. And that's the right file. Okay, so let's do the same here. Instead of invoke, we'll change that to a call. And then we've got some things to do here, so we're going to move into RAX, output file handle. What was the second one? It looks like it's RDX, so we're going to move into RDX, the offset. And what was the name of our string? So all we're going to do is we're just going to write this string. So it's example string. Okay, the third argument is the example string length. So we're going to move into, and that goes into R8. Example string length of, I believe I called it. And then we have to say, we have this total written thing. Now, ADDR is used by invoke. It's not something that you would use in a call. So we're going to have to use a offset. Oh, it should be R9. Now we haven't defined that variable yet, but let's do it. And then, because we're done with our 4 arguments, we now have to go into the stack. And now we've got our 5 arguments. And then we can say call. So let's go ahead and define the total written variable. Let's do that up here. Total written, define quad, and uninitialized. Okay, no errors. So let's go ahead and run this. And I'm just going to say debug, start without debugging. We get a welcome, everything looks good. Okay, so now this is where Visual Studio is a pain in the neck. I'm going to right click on the solution, say open file, folder in File Explorer. And I'm going to go looking for that file. And it's not there. I always have the same problem trying to find it. Okay, let's go to x64, debug. Well, maybe it wasn't created. Let's go ahead and check this. We didn't really do anything if there was an open error, so let's go ahead and debug it. I'm going to put a breakpoint right here and debug it, and let's make sure it opens okay. Let's look at registers. Oh, it didn't open correctly. We have a problem. And the reason I know is because this is a negative number. So if it's less than, and that's the problem right here. We said equals to, so it doesn't actually jump. So we've got a problem here. Got a couple of problems. So let's go ahead and say jump if less than 0. That means it didn't open it correctly. And then we're going to go ahead and save it. Now we didn't do anything in the open error. We just have a no op because we can do that take a look at that in the debugger. So why are we getting this open error? Let's take a look at that. So I think the problem might be our first argument. You're not supposed to use RAX as your first argument. You're supposed to use RCX as your first argument. So let's go ahead and change that. On all of them, we're using RAX. See, it's really different. Let's go ahead and build it. All right, looks good. Let's run it. Oh, here it is. It hid it from me. All right, now let's go ahead and find that file. Once again, I have trouble finding it. There it is right there, text file. I'm going to double click on it, and I'm just going to open it in Notepad, and you can see the data. There's no new line, so okay, so it is quite a bit different. It's a little bit more, it's a little bit closer to Linux, but the registers are different that you use. You really need to put all your comments in there. And so the next thing I want to do is I want to show you about in Windows how you would do end of file. So what we want to do, what I'm going to do is I wrote this out to the file, this string. Now what I want to do, like I did in Linux, is I want to go one character at a time. I want to read one character at a time from the file. And by doing that, we can take a look and see just how important end of file is. Okay, so let's go ahead and copy all of this again. So that created the file. Let's go ahead now and paste it. And now we're going to read the file. And pretty much everything is the same, except for input, you're going to change this 40 million to 80 million. R80, everything else is the same. Instead of 2H, you're going to say 3H. And let's go ahead and comment some of these. The file name. And this is access mode, generic read. I will put all of these values into the description of the video. This is do not share. This one is no security needed. 3H is open an existing file. 80H is file attributes normal. And 0 is template file handle. We're not going to use that. Now I didn't put those comments in the one above it, and I really should, because they're really important for self-documenting, and also you can always look back at your code and see why you did something a certain way. So let's go ahead and do that. The file name. Now this one, 40 million, is access mode generic write. 0H, do not share this file. No security needed. Okay, let's make sure we get the right values here. 2H means always create. And what that means, it means that if the file is already there, overwrite it. And that's fine for this. 80H file attributes normal. And you could have done some copy and paste here for your comments. Template, file handle, not used. Okay. And what are these comments here? This is the file handle to write to. The address of the data to write. Length of this data. The how many characters, or I should say bytes, are actually written. You don't fill that in, the call does. And this last one is, I believe this last one is template. No, that's not template. What is it? That's the address of total writtens variable. Oh, this is just not used. All right, great. Okay, so now we want to read the file contents one at a time. We're going to open it up, and we're going to check to see if it opened. Okay, and instead of output file handle, we'll change this to input file. Okay, so that opens it up. Now the next thing we want to do is we want to process it. Now we're going to have to change the close to close the input file handle. And now let's process the file contents. So what does the read look like? So let me see. We've got the RCX. We're going to move the input file handle into RCX. Now, where do we want to write it to? That's what goes in RDX. So let's go ahead and create a variable up here. Let's call it read buffer. And let's say, define byte. And I like to do like 64 bits or so, so let's go ahead and do that. So I'm going to say define byte. Let's say it's 64 bytes. I said bits, I meant byte. And let's just say question marks. Let's make sure we have that syntax right. All right, looks good. Oh, we didn't specify where we're going to put it. So I believe that goes into, yeah, I've got some of these wrong. So in RDX, we should do the offset of, I don't know, what was it, read buffer? I believe that's what we called it. So yeah, I was doing something else there. Where to read it to. Total number of bytes. Yeah, that was positioning. I'm sorry. So let's go ahead and move R8. How many bytes to read, and where should the read result go? And what that means is the number of bytes actually read. And we don't need this right here. Instead of read file, we're going to say, or write file, we're going to say read file. Call read file. We're going to move into RAX. And I say here total written. Let's create a total read, because we're not really reading or writing, we're reading. So let's go ahead and go total read. And then let's compare that with 1. Jump if not equal to 1 to read error. Now let me go ahead and create read error right here. And let's talk about what that is. So what we want to do is we want to check to make sure the number of, actually let's not do that. Let's just go ahead and delete that for right now. And we're going to read the file, and then let's go ahead and print it. Okay, so I'm going to push the read buffer. I'm going to push RAX, and then I'm going to call print text, and then call print NL. And this is simply print the character read from the file. That's all that is, and that's using the Komanetsky functions. Now we need to put that into a loop. So I'm going to create a read loop, and I like to indent things. And then we're going to jump to read loop. Now if you watched the Linux version of this, the Linux half, you're going to see that there's a problem here because we're not checking. Okay, so let's take a look at what we did here. Oh, yep. You really can't do this. Let's say in Windows, you can't do it as easily. That won't work either. You have to move the offset into a register. So we're going to move into RSI the offset of read buffer. And then you need to push RSI. Let's see how that builds. Oh, total red, so we never actually created that. So let's go up here and do that. All right, good. Okay, so let's quickly go over what this code is doing. So we open the file for write. That's the first thing we do right here. And we've already tested that. That works. We write the string to the file. That works. We close the file because the file was open for output. Now we're going to read the file one character at a time. So we open the file for input. We're assuming that that works, but we're going to test it. We then have a loop here where we read a single character from the file, and then we're going to print it. Now, how do we know we're at the end of the file? Well, we don't have that in there yet. And let's see what happens when we run this. So let me go ahead and build it one more time. And let me debug it. Actually, I'm just going to start without debugging. And, well, it looks like we got a problem. Definitely we have a problem. So let's double check all of these values that we've got here before we move on. And so the file name is correct, the 80 million is correct, 00 is correct, 3H80 called create file. And it is weird when you open a file for input, you're still calling create file. It's these values in the stack and in the registers that say how it's going to do it. Okay, open error. I done jump to that, so it kind of looks like that worked. Okay, okay, so how do you read the file? Well, we go ahead and move the input file handle to RCX. RDX is the offset of the read buffer. Now, yep. So RCX, RDX is the offset of the read buffer where we're going to read it into. R8 goes how many bytes we're going to read. We're only going to read one. R9 is the total read. We call read file. All right, that's good. And then let me double check this. We move the offset of the read buffer to RSI. We push RSI. We move one to RAX. We push RAX. We call print text. All right, let's go ahead and debug this and see where the problem occurred. And let's do it on the create file. Okay, so let's press continue. All right, here we go. So here's the create file. All right, good. So RAX looks like a valid value for a file handle. So it looks like it created it okay, or it opened it okay. Okay, everything looks good. All right, now the read loop. So let's put the file handle into RCX, the read buffer into RDX, 1 into R8, 1 byte, R9, offset, and we're going to read file. Now let's go take a look at the read buffer. So we're going to go to memory, and I'm going to type ampersand read buffer. And we're looking at bytes. That's cool. So let's see if it reads it. Well, we definitely have a problem here. The program died on the first read. Not really sure why. Let's take a look at why that might be. Let me end this. All right, I think what happened here is we forgot to put on the read. If you take a look at the read when you call read file on 32-bit, we had a fifth argument which was 0, and so maybe that's it. So let's move a keyword ptr rsp plus 32 0h, and we're not going to use it. If you remember on 32-bit, when we called read, or when we invoked read file, we had the input file handle, we had the read buffer, we had 1, we had total read. I mean, everything was there. We also had 0 as the fifth argument. Well, we didn't do that, so let's go ahead and try that now. Yeah, I left that out for some reason. And let's go ahead and run it. So I'm going to say debug, start without debugging. All right, that looks better. Well, it doesn't actually look better, but it looks like we're in an infinite loop just like we were in Linux. So let's go ahead and Control C out of that. And why do we have all those E's? Well, if we take a look at the string that we're printing or that's saved on the file, the last character is an E. So nowhere in there did we check to see if we were at the end of the file. So what I'm going to do is, in this code before we print it, I'm going to check to see, did I actually read a value? Did I read a value from the file? And that's how you do it. So we're going to compare RAX with 0. Now, why am I comparing it with 0? Because, and that's not a compare, that's a DMP. I'm not sure what that is. So every time you read data, you check to see if the total read. Now, we can't do that. I have to move into RAX total read. Because remember, this argument right here, the fourth argument, says where should I store where I read the data? Where did I read it into? How many values did I read it into? How many bytes did I read? That goes into total read. In Linux, that doesn't go into a variable, it goes into RAX. So we're going to move that. Check to see if end of file. If that's 0, so I compare RAX with 0, if 0 bytes read, then AOF. So if that's true, if I say, so I'm going to say jump equal to end of file. We haven't created that label yet, so let's go right here. Here's my end of file label. All right, let's go ahead and build that. And let's debug it. Well, that looks a lot better. That looks just like we did it in Linux. So it printed one letter at a time, and then it went ahead and ended the program successfully. So Windows is really a lot different. When you're calling functions in 64-bit, they really changed it a lot. It's more like Linux. But instead of pushing things onto the stack for arguments, you put them into registers. Well, I guess you do the same thing on Linux. And but there's not if you have more than 4 arguments in Windows, you put them into the stack using the move statement, not the push. Okay, so that's checking for end of file. That's some 64-bit file I/O programming. After this video, I'm going to do a video on advanced file processing, which is random access files. It's kind of cool. We're going to take a look at that. Until then, you take care.